That's our plan. Last time I gave you guys this sheet of multiple choice AP questions. Yeah,
are we going to have an optimization?
Yeah, probably next week. That's probably what we're looking at. Like end issue next week. Okay?
It's gonna be end of next week is the practice.
Optimization. The optimization thing. And then probably the week after that we're looking at the test sims. Okay? The format for the optimization would be the same as the related rates. So give you like 5 multiple choice and then 3 free response. You pick 2 to do. Would be the format. I've written it. I need to proofread or whatever still.
When did you put us?
Probably end of next week. End of next week. Does that feel okay?
Yeah.
Yes. Optimization. Maybe. It's either Wednesday or Friday. So we'll figure that out. Again, I'm open to your guys' scheduling concerns there, where it doesn't matter to me a whole lot on the date. I'm ready when you're ready. Hey,
What's our virtual day work going to be?
it's going to be some 6-3 problems, so nothing new.
2 weeks.
I think 2 weeks.
So test 6 would be then
That's what it sounds like.
And then after Irish Week, we have no.
I think that sounds right. Yeah. Okay. Any questions on these guys? We have time to do like 1 or 2 of these. Yeah. Alice.
Number 5.
5? All right. It says, let R be the region in the first quadrant bounded by the graph of y equals negative x, the x-axis, the y-axis, and the line x equals b. Region R is the base of a solid whose cross sections perpendicular to the x-axis are squares. If the volume of the solid is 4/9, what is the value for b? So I'm going to just kind of sketch myself a little bit of a picture, although it's not like super duper necessary. So e to the x looks like this, right? So e to the negative x is going to look like this, right? It's just going to be like a reflection across. So it'll be like this. Now this should be the point 0, 1, right? We have our line x equals b. So this is like our shaded region, right? Everybody feel okay there? Okay. And we're told that the cross sections perpendicular to the x-axis are squares. So like that's my side of a square there. So my volume should be the integral from 0 to b of e to the negative x squared dx. Does that all look okay to everybody? Okay. So we know the volume is 4/9. And then we need the integral of e to the negative 2x dx. To find the antiderivative of that, I need to use a u substitution. Oops. And I suppose I could, let's do this. That'll probably make our lives a little bit easier. So I'm going to adjust the bounds in terms of u. That'll save me like a bunch of back substituting in since I have to solve for b anyways. It doesn't, Okay. My antiderivative is just e to the u over negative 2. So far, so good. So that's going to be e to the negative 2 over negative 2 minus e to the 0 over negative 2. Where is I have a negative sign wrong someplace? Because I add that over. Oh, so I subtract that. There you go. Okay, so that'll be fine. Okay. So this is e to the negative 2 over negative 2 plus 1/2.
Does the b matter? If there was a b.
Oh. Thank you, Lucia. Yes, absolutely. That's what we're solving for.
Yeah. Okay.
And now I'm going to subtract 1/2 from both sides. Okay. So that's like 8/18 minus 9/18 equals e to the negative 2b over negative 2. So that's negative 1/18, right? Now multiply over by the negative 2. So that'll be positive 1/9. And then I just need to solve for b here, continue solving for b. So we'll take the natural log of both sides and then divide by negative 2. And I'm guessing we don't have exactly that here, but this is equivalent to it, right? So I've pushed the negative sign into an exponent, which makes the reciprocal of 1/9. So it should be this guy right here. That was a rough one, Alice. Again, did you get there?
Yeah, I got confused and like tried to. I understand.
But if you're able to get to here, that's great, right? That's great. That's what you're going to need to be able to do.
Yeah.
Is get to the volume piece, get the setup correct.
Yeah, I was confused about the bounds because it wasn't given, so I just didn't know what to do.
Yeah, so drawing the picture really helps, right? Like that we're just slicing, so it's going from 0 to 8. Peyton?
I have one general question and then a casual question.
Okay, hit me with the general.
For when we're like subtracting, like a number 4, when it's the picture of the graph or whatever, and you're trying to figure out which to subtract from which, is it the bigger one minus the smaller
So
one?
if it's a vertical, then it's going to be top minus bottom. If it's horizontal, it'll be right minus left. So yes, the bigger number minus the smaller number.
Okay. And then I just had a question, or could you do 7?
7. This will be our last one from this sheet, and then we'll move on. It says the base of a solid is in the region in the first quadrant, bounded by the x-axis, the y-axis, and the graph of 4 minus x squared. For this solid, each cross-section perpendicular to the x-axis is a rectangle, whose height is 6 times the x-coordinate. What is the volume of the solid? So I'm going to go ahead and sketch myself a little picture. So we know we're bounded by the x and y coordinate, right? Or axes. And then I have here draw the part of my graph in that first quadrant. Everybody okay with that?
How do you know the height is? How do you know the height is 4?
If I plug 0 into x, I get. Is that good? Okay. All right. Okay. So the area of the rectangle is like base times height, right? Everybody's okay with that? Okay. This is base. Well, it says the height is 6 times the x-coordinate. So I assume that's not the piece that's drawn in the plane.
Okay.
Right? I think that to me looks like the base. The height is 6 times the x-coordinate. That's just the 6x. And the base here is just going to be that then, right? It's the y value of that, the height of that thing. So my volume should be the integral from 0 to 2 of base times height. Does that feel okay?
Yeah, I was just confused with how you get the base and the height.
Yeah. Yeah. So we can do 6, 0 to 2 of 4x minus x cubed dx. So 6 times 2x squared minus x to the 4th over 4 from 0 to 2. Yes, I distributed the x through, yep, and pulled the 6 out to the front.
Oh, okay. And then you do the antiderivative.
And then I did the antiderivative. Exactly right. Mm-hmm. So I'm going to have 8 minus 4 and then thankfully 0. So, that should be 2 to the 4th. So that's going to be just 4 and then 0. So we have 48, it looks like. Oh, yes, 24. Thank you. I was going to say, well, I did something wrong. Like, why is 48 not on the list? It's because you did the easiest part of the problem wrong. I started like 6. 8 minus 4 is not 6. Thanks, dude. Emma, looks like you're going home early today, huh? That's nice. You're welcome. Make you feel better on that?
Yeah.
Okay, so moving forward, today, I'm going to talk about another way of calculating volume for one of these solids of rotations. So again, the previous piece that we've just been doing, no rotation was happening, right? Here we're back to rotating about an axis. We're going to show you why it was necessary for us to cook up another way of doing this. It's not a shell or not a washer or a disc. Okay? So sometimes these disc and washer methods can make the problem absurdly difficult. Okay? Almost in an intractable way difficult. So let's look at this example. So here we have some function. It's y equals 2x squared minus x cubed. So this is the area under the curve, right? And we're going to rotate that area about the y-axis. So you're going to end up with a hole through the middle, right? Or at least an indent through the middle. Everybody's okay with that? So it's like, okay, well, it's a washer problem, right? So first issue, my inner radius, my outer radius. What are you noticing about the two? Both on the same curve. What do I do with that? Still possible. Now it's a pain. What would you have to do? You'd have to break it into like two areas at the maximum and find the volume of rotation for this piece, for this half, and then do the volume of rotation for the other half and add them together. Pain, but doable. How would you find this value where it's at a maximum? Use the first or second derivative test on this function. Like, okay, this is a hassle, but like, it's more work. It doesn't make it hard, right? It's just like more effort. But here's the bigger problem. If we're rotating about the y-axis, we need these in terms of y, right? So I would need to rewrite y equals 2x squared minus x cubed to get the in terms of x, right? I have x equals, what type of an equation is this? Cubic, right? That's a cubic polynomial. Do you guys have a good way to solve a cubic polynomial? If it was a sum or difference of two cubes, sure. This is not, though. This is 2x squared minus x cubed. Yeah, right? This is the problem. This is what makes this problem virtually impossible for us to attack as a washer disk problem. Is because now I need to try to solve a cubic equation, a cubic polynomial, and there is a general equation, like cubic equation, like there's a general quadratic equation. It sucks. And here's the worst part. If this was degree 4 or higher, I think degree 5 or higher, there is no closed formula to solve a polynomial in those higher degrees. It's actually probably proven there can be no closed formula for those, and so you're really in a pinch. Is everybody okay? So really the problem, while it's a hassle, the fact that the inner and outer radius lie on the same curve, the bigger problem is that trying to solve this polynomial for x. That's the real sticking point where like makes this problem kind of impossible for us to do. So what we're going to do is we want to cook up a better method. A better method to deal with something like this where we end up with either a situation where both the inner and outer radius lie on the same curve, which stinks to deal with, but like, it's like more work, but like, ugh, there's a better way. I'd rather do that, but I can. We have all the tools we need to. It's a lot, but we have the tools. Or to solve this for x is just like an intractable problem for us. We have another method. This other method is called the shell method. And the idea is essentially like peeling an apple, right? So like you can take an apple and you could calculate its volume by peeling it, and you end up with like a rectangle. You could find the volume of that rectangular solid, and you could keep peeling it, and you get these different size peels, and you could keep calculating the volume for each of these peels and add them all up. Okay? It's kind of like unwrapping a present. You guys have watched Bluey? My daughter is so like this. But there's one where like they do like a pass the parcel where there's like a bunch of layers of wrapping paper around a present, and each kid like unwraps one layer. The same idea. Like we're pulling a layer off, calculating the volume of that layer, pulling the next layer off, calculating the volume for that layer, and adding up those repeated volumes. Okay? So the question is like, what kind of shape are we going to do this with? Why are we going to be getting rectangles out of this? And the idea is we're going to take like a hollow cylinder, and that's going to be like our shell. So when we unwrap that hollow cylinder, if it doesn't have a top or bottom, it's a rectangle, right, when we unwrap it. And the thickness of that that cylinder is just going to be like our dx or dy, right? It's going to be infinitesimally thin. We're just going to add those all up. So our formula here is really going to be circumference of the circle times the height, because that's the lateral surface area for a cylinder. I have some pictures here that help us envision this. So this is kind of the shell that we're going to be making every time. It's going to be like a hollow cylinder where we have like some inner and outer radius, but the difference between those inner and outer radius is just like infinitesimally thin, right? So our volume is just going to be, for that one particular shell, it's going to be 2 pi r, the circumference of our circle, times the height, times the thickness, that's the delta r, which will become a dx or dy. Okay? Don't worry about copying all of this. It's just to give you an idea of what we're doing. We'll show you like the whole thing here in a minute. Another way of looking at it, so here's like our curve. Here's like the shell, whose height of the shell is the same as the height of the curve. We unfold it. So the radius here is x, so we have 2 pi x as the circumference. F of x is the height, and this delta x, or this dx, eventually, will be like the thickness of these shells. Does that feel okay? Visualizing what you're doing. So like, let's say we have this is our function, and we're rotating about the y-axis. We're going to get some kind of three-dimensional shape that kind of looks like this, like a plunger kind of shape. What we're going to do is we're going to build these shells, these cylindrical shells, where the height of the shell is like the height of the function, and the radius is like the distance from the axis of rotation to the function. And we're going to, take those shells so that like eventually they're infinitesimally thin. So you get something like this. Does this help visualize what it is that we're doing? So the formula, oh no, it's doing this again. One moment, please, see if it wants to respond to me. I don't know why we're so stubborn. Some days this works just flawlessly, and other days like I can't do a thing. It just wants to fight me the entire day. Was this the class that was fighting me on so hard last time? Oh. Yeah. I'm already sick of waiting. So impatient. It's doing something here. Oh, maybe it was getting worse. Let's try. I didn't even write anything though, guys. We're just scrolling, which is really the frustrating part. No, this is what I want in transform. Try doing this real quick. So, if we take that solid from figure 3, our integral for volume is going to be the integral from a to b of 2 pi x f of x dx. It's kind of our general format, where like x is our radius. Now this x could change, right? It's not always going to be x, right? Because you could rotate things about the x-axis instead of the y-axis, and then that x would be a y. And depending on what the function is doing, that distance might be for rotating to not the y-axis, right? It could be the distance from the axis of rotation back to the function. So it could be like 1 plus x or 2 minus x or something. We'll look at some examples though, to kind of clarify that. But this is the general setup. All right, let's return to this original problem that we started with, that we saw that was going to be like kind of impossible to do using a disc or a washer. So frustrating. I just tried to write something. You know, like, what did we do? We did nothing. I zoomed in and like wrote a V, and then was like, maybe I want to write a different letter here. And then it wants to fight me about it. No. Okay. All right. So this is like my radius of my cylinder. I'm sick of this. Why is it just makes me so upset? Why can't this just work? What are we doing, OneNote? Why is this such a problem? So I just want to write on this and like occasionally erase something. Okay, so we have this, right? Okay. The x is our radius, that's what's going to be changing, right? So the x varies from 0 to 2. So I know we're integrating from 0 to 2, and because the x is the coordinate that's changing, that's my radius, is based on x, we're going to be integrating with respect to x. Now the base of the rectangular prism that we're getting when we take the cylindrical shell is 2 pi r, and our r in this case is just x, times the height of our rectangle, or rectangular prism I guess I should say, which is just, in terms of x, 2x squared minus x cubed. And we're done with this. nothing was interactable, I'd have to solve for x and have to like break the thing into two chunks. When I get something where it's like a function that's like not one-to-one, or the area that's not one-to-one in the direction that I'm rotating, shell method is probably your better bet. Now, real talk for you guys, on your AP exam, you're going to find no problems that are easier by shell method than they would be by disk or washer. Your AP exam does not expect you to be able to do the shell method. Now, your first year or second year calculus course, when you do this, your professor certainly will. I will certainly expect you to be able to do both, and I will give you situations where you basically have to be able to do the shell method in order to get the volume. Okay, and we'll do some practice here. Part of your 6-3 or your virtual day assignment is to do some practice where here's some situations that are all mixed up, volume or shell, right? Because that becomes the hard part, right? Or should I do disk or shell or washer? What am I doing here? Now, real talk, there's no situation where I would use a disk where a shell would be better. They would be the same level of difficulty. Usually disks are easier to see than it is the shell. I would just do a disk every single time if I'm doing a disk problem. If it's a washer problem, maybe a shell would be easier if you run into a situation like this where the function is not one-to-one, where the radius is going to clip both parts of the function. I'm probably just doing a shell and not thinking about it past that. Okay. And at this point, I'm not going to bother doing this by hand. We would know what to do, though, right? You know, pull the 2 pi up front, distribute the x through, antiderivative, plug back in. And you could always check then with your calculator. Let's keep going and do some more setups, okay? All right. Here the direction says use cylindrical shells to find the volume of the solid obtained by rotating about the x-axis. The region under the curve y equals the square root of x from 0 to 1. For the reference, I would never do this problem by shells. Think about what's happening. Right? We're rotating about the x-axis. What you're getting is like a dome, but it's like facing sideways, right? Instead of up and down. I would just disk this, right? Super obvious what to do with disks. I don't have to rearrange anything. Like it's an easy disks problem. Now, we're going to do this as a shell problem for the sake of doing it as a shell problem to show you the difference when you rotate one way versus another way. But I don't know why you would want to ever approach this as a shells problem and not a disks problem. Everybody okay? But the point right now is getting comfortable with shells, so I don't want to pick any functions that are too complicated to deal with. You know, anyway. So here we go. So this is our picture. Y equals the square root of x from 0 to 1 and rotating about the x-axis. So in this case, the radius is going to go from the axis of rotation to the function. That's like my radius. That is a y. Why? What is the problem? What is the problem? I drew one thing and then I tried to write a V. I'm not even that far zoomed in. Oh, it was the R that was the problem. Okay. So if I think about it, my smallest radius would occur here, right? Where the radius is basically going to be 0. And my biggest radius is going to occur at the end, where the radius would be 1. Everybody's okay with that piece so far? 2 pi. And then my radius is this y coordinate, right? So I need to take the equation for y equals the square root of x and get it as x equals. Are you okay with that? Set this over here. Now this distance is going to be like my height. So it's going to be from like inside the shaded region. So my cylinders are coming out like this way, right? Can you see it or no? So like my first cylinder is like here, and then like my next cylinder is going to be like here, and my next cylinder would be like there. They're opening this way. So like the height of our cylinders are coming back that direction. That was kind of messy, but I think it helped, right, in visualizing what's happening. The way I remember it is the height of my cylinder is always going back through the shaded region. Okay? Should always be going through the shaded region. I would never want to draw my cylinder out here into the unshaded space. And the height of the cylinder, should always be parallel to our axis of rotation. Right? The radius is perpendicular, height is parallel, both of which should be going through the shaded regions. Is that something? So if I think about this distance, this is going to be, the distance from here to here is 1, right? And the distance from here to here is x. So that distance h should be 1 minus y squared, because I want it in terms of y, not in terms of x. Well, it's like 1 minus x, but x is equal to y squared, right? Because I'm integrating with respect to y. Does that feel okay? And then distribute things through and do our antiderivatives and plug things in. That's the setup. It's okay if I hand wave through the integration in the interest of kind of like doing more setup. I feel like the setup is the hard part at this point now. We feel much better about the integrals after doing some more practice on that. Okay. Does this feel okay? Again, for the record, would I ever do this using shells?
No.
Me personally, never. This is screams just do a disk. And it's super obvious, right? You know, it's like, and I'm done. Right? Like easy disk problem. But whatever. All right. Let's look at another. So we are finding the volume of the solid obtained by rotating the region bounded by y equals x minus x squared and y equals 0. So we're talking about that region here, about the line x equals 2. I look at the setup of this problem. If I try to do this with a washer, the inner and outer radius would be on the same curve, right? Everybody's okay with that? That's my cue that I should do a show. Is everybody okay? So the inner and outer radius would both be attached to y equals x minus x squared. So I'm going to want to do this as a shell problem instead of a disk problem. Now I can do it, I should say washer problem. I can do this as a washer problem. I can. Like Mr. Kulik is capable. It's going to be a colossal pain in the ass and take pain in the butt, and take way more time than it would be to just do this as a shell. It's possible for us though, because I can solve this equation in terms of x. It's going to stink though, right? You're going to have to do the quadratic formula basically where c is negative y. And now you're going to have like a terrible expression and the integration is going to be just not a lot of fun. But like it is doable in a way that the previous problem wasn't, but it is unpleasant. Okay. So, start my situation. I want to draw in a picture of where my radius is and where my height is. So my radius is going to go from the axis of rotation back to the curve. That's my R. The height is going to be drawn through the shaded region, so that's like the height. Okay. Notice that I'm not trying to draw the cylinders in here. They're really hard to draw well. I don't care really what they look like beyond like enough to know like where to draw the radius and height at. Is everybody okay with where I chose those at? Okay. So the radius so here I'm going to be integrating with respect to x, right? So again, the radius is going to be changing based on the length there. So integrating with respect to x. So dx. Now, the part of my radius here is going to be, so the distance from like here to here is 1, right? Yes.
You just said this, but I didn't hear you. You said that we could choose anywhere for the radius and the height, like on the curve.
I'm just drawing an arbitrary
Okay.
one. There's nothing specific about this location that I chose.
So it doesn't matter, like where you are.
Correct. I'm just kind of drawing it to visualize what's going on. Is that?
Yeah, that makes sense.
Okay. Okay. So I know from like, how do I just say this? So we know here to here is 2, right? And we know from here to here is like x, right? So radius is 2 minus x. Everybody feel okay there? Now, let's think about our bounds of integration. The biggest this radius could be is 2, correct?
Yeah.
And the smallest the radius could be is 1, right? So my x needs to vary from still 0 to 1. Right? When it's 0, that's the radius of 2. When it's 1, that's the radius of 1. Is everybody okay there? And the height is just going to be the y coordinate at that point, correct? which is just the function. And now you have a little bit of foiling, but like the antiderivative is easy. The integration should be relatively easy. Hey.
It's so the bound should be based off of the radius,
Mm-hmm.
not like the wall. Okay.
Yeah, that's the way I think about it. Is I'm thinking about, more often than not, it's just like, you know, the function, and I'm looking at, you know, like the x's or y's that the function is defined over.
Yeah.
But I usually think about it as, what's my biggest radius, what's my smallest radius, and make sure that that matches what I'm seeing here, which in our case it did, right? Where r is between like this, and if r is 2 minus x, right, I'd subtract 2 from both sides. I'd have like -1. And then when we divide, we get 0 to 1. Does that make sense? So I'm just kind of confirming that. But usually I find it more intuitive to think about the radius and kind of coming up with the bounds, at least when the radius is different than just x. The radius is just x or just y. Bounds are easy. The radius isn't, just want to be careful. Right? I want to think a little bit harder and make sure that my bounds match physically what's going on, what I'm trying to do. How did you guys feel on this? Again, similar to the discs and washers, right? You're doing kind of the same thing. The big difference is instead of the formula being pi r squared or pi r squared r1 minus pi r squared r2, this is 2 pi r times h, right? So I think I have a couple of these that I've just pulled out of the homework to do some more example on, if you guys are up for it. So if you look at 3, that's the picture I've drawn below. See if you can get the setup there. And we're revolving around the y-axis, it says. So take a minute. There's the picture. This is the info. So this is like your shaded region. Okay, rotating about the y-axis. Try to set up the volume for this. Don't worry about computing the integral. Let's just worry about the setup. And see if you can come up with the correct setup. I'll wait here for a few minutes and then kind of go through the setup. Sound good? We're always drawing the radius from the axis of rotation to the curve, and we draw our height through the shaded region to the boundary. You know, usually an axis or a line or something that's the boundary, usually a straight edge. So here the radius is just x, and the height is just f of x. It's like the classical, easiest possible setup. Notice that if you wanted to do this the classical or the other way, you could do this with, but you need a washer to do this. You get a little bit messy, but still totally doable. This was much simpler. Alice?
Why is the radius x and not 1 minus x?
Because the radius is being drawn from the axis of rotation. So we're going, the radius would be like here or here, and that distance is just x, right? We're going x over. 1 minus x would be those distances, right? That would be if you were rotating about that line.
Okay.
Does that make sense? So just kind of not wrong, but just not this setup, right? If we were rotating about x equals 1 and not the y-axis, then you'd be good. Good question, though. Teacher?
Why is it dx if we're like rotating the y?
Because the thing that's varying is the length of the radius, right? That's the thing that's changing with each cylinder. And that length of the radius is a horizontal distance, which is why it's an x that we're integrating.
So is that like
It's like the opposite of what the discs and washers was.
If
Yes.
we're rotating on the x, it'd be dy.
Yes. Yes. If you're doing a shell, the dy and dx rule is like opposite the disc and washer. Yes. 100%. Good observation. Let's see, what is this one? I'm not sure which one this is. What is this? Oh, that's got to be this guy. So that's what we're doing next, I think. Yes. Yeah. I'll copy it down here in a second. So there's your shaded region between 0 and 1, rotating about the y-axis still. That's the name of your function. Take a minute, try to set it up. I'll go through it in a second. Or at least write in the answer if there's questions you can ask about this, like we did last time. So there's like my R and H. Same exact problem essentially as the previous one, right? We're just R is X and H is F of X.
Just checking to solve this, you would have to use U substitution.
Correct. Yes, this is solvable by hand via U substitution. The U would be negative x squared. So you have a 2x dx in there, so you're going to be able to,
And these problems in the homework, are we just going to be like setting it up like this or solving that?
I don't remember what the directions asked for, but what I would tell you, Aaron, in terms of like, so it asks you to find the volume. So I would say that like, if you are confident on your integration, you just type these in the calculator, press enter, and see, make sure it matches the answer in the back of the book. Because I think I assign mostly just the odds here. If you're like, I still don't feel great on my integration, I should practice some of this, or just do enough practice to where you feel like, okay, I'm still sharp here. You can do a little bit of it, but you wouldn't worry about it. So on the test 6, in the volume section, that'll be the no calculator section. Or, I'm sorry, will be the calculator section. And I won't expect you to do any of the integration. Okay, there'll be points for the setup and then points for the final answer. But it's just like 1 point for each aspect of the setup and 1 point for the final answer. Just getting into the calculator, hitting the right answer. Kind of thing. There will be other integration that you have to do by hand, but not the setup. And then I'd rather have you be able to do more volume. You can't do a lot if you have like 5 minutes of integration by hand to do at the end of that. Hey.
Will the height always be the function itself? Like that function height or?
Well, could it change? Yeah, if they were like crappy about it, probably not in your circumstances.
So like h is kind of always the function, even on like.
So like if in this problem, instead of it being bounded by like the x-axis, what if it was bounded by y equals 1? So now the shaded region would be this. So the height would be f of x plus 1. So you could do something like that relatively easily, and now the height is just like the function plus or minus some constant. We can do that fairly easily, and I think it's still well within your capabilities of being able to do something like that.
Yeah.
So I would say not necessarily, but does that feel okay?
Yeah.
Mm-hmm. And like again, like I didn't give you this. I don't think the textbook has anything like this. But like, you know, the other place it could happen is like, you know, if you had like some second function coming through and your shaded region is now like the bound between the two. So now h is going to be like top minus bottom function.
Yeah.
Where now it's like the difference of two functions, but it's usually still like the function values is what matters.
Okay.
Is that what you're asking?
Yeah.
Okay. Yep. And again, that's fair game. It's not much different. All right. Same story, but this time we're going about the x-axis. So this first example is the first one. So we're between, this is our shaded region, and this is the curve xy equals 1. But this time we're rotating about the x-axis, which means that our volume is going to be, Adrian? dy. So start with that image for everybody. I wrote everything you needed, right? Like y equals 1, y equals 3. There's the equation for the function. There's the shaded, like about the x. I tried to draw it all in for you so you didn't need the piece from above.
Thank you.
Yeah, no problem.
Why are we going
So let's think about the radius. So the longest the radius could be is 3, right? And the shortest it could be is 1. And if the radius is y, is the y coordinate, 1 to 3. Is that
Yeah.
right? Like it shouldn't be 0 because you can't have a 0 length radius because there's no radius that's between 0 and 1. The first radius starts at 1. Is that?
Yeah.
Okay. So again, like I'm thinking hard about the bounds in terms of radius, especially when like my function doesn't butt right up against the axis that I'm rotating against. Does that feel okay? And notice that the integral here is going to be super easy, right? It just becomes the integral of 2 pi. So it's going to be, the answer be 2 pi. Right? Or I'm sorry, no, it'd be 6 pi minus 5 pi. 6 pi minus 1 pi. Is this feeling okay? Comfortable-ish? Oops. All right. And again, now we're mixing them together, right? Now instead of it just being a block of everything is rotated about the x-axis, everything rotated about the y-axis, here's some examples where like some of them are x's and some of them are y's, and you have to make sure you're being careful about whether it's a dx or dy problem. But that's basically what the homework set looks like, are these odds from these 3 sections. Okay. Your virtual day assignment is going to be from the same section, but I think it's like 57 to 62 or something. There's like 8 of them, maybe, something like that. And they are disc shell washer. Like, make your choice which one you want to do it as. They're not going to instruct you. They're not going to tell you this one should be this way or this one should be that way. Right? Almost any problem that is a disc or a washer can also be done as a shell. The reverse is the place where it's not really the same. Right? The ones that are best done by shells are lousy disc or washer problems. When anything done by a washer, I don't really only use a washer, most likely. It's usually easier than setup-wise than the shell is, at least to visualize. Does this feel okay? So we'll circle back when we get back from the little mini conference break and do some more volume stuff, do a day of volume practice, where I just give you some volume problems to work out in pairs and like let you guys struggle through that, right? To struggle us together and like get better at it, which I think is oftentimes what you need is just some time. Like you have to sit down and practice by yourselves and like get some stuff done, and ask some questions, and get some feedback, and start getting on the right track with this stuff. The last 15 minutes or so that we have here, do you guys want to talk some op? If that's coming next week.
Yeah, especially at 7. Yeah.
Let me look at my op problems. You guys have your op stuff, you can take that out. Yeah, of course. All right, what do you guys want to... David, you said you wanted to look at some stuff from Op 3.
Yeah.
we'll start there. I'll tell you straight away that 4 is the worst one, I think.
You do that.
So it says a rectangle is inscribed in a circle of radius r, and we want to find the maximum possible area in terms of r. So this is I thought the hardest part about this one was going to be the initial setup. So what I did is I embedded my picture inside of the XY axis so I could turn this into like a coordinate geometry problem instead of a geometry proper problem, which felt like it was going to be a lot harder. No. Why would you think that I would want to? Okay. So there's like my guy, and that's like my radius. So this is like the point xy. This would be like x negative y. This would be like negative x, negative y. And this would be negative x, positive y. So far, so good. So that's going to be like my setup. I know the area for my rectangle is basically length times width. So let's call this side length and this side width. So length is going to be basically the distance between negative xy and positive xy, which is just 2x, right? And width would be the distance between positive xy and positive x negative y, so just 2y. So far, so good. Now, I'm going to want to choose now to rewrite these so that I've eliminated one variable. I just want to have either x's or y's. It doesn't really matter to me which one I do, so like I'm going to just go with x's. So if I look at this part of my picture, that's a right triangle with radius r, right? So I have like x squared plus y squared is equal to r squared. So y is plus or minus the square root of r squared minus x squared. And since y is a distance, I can drop the minus, and this will just be 2 root r squared minus x squared. So my area function in terms of x is going to be 2x times 2 root x squared minus, r squared minus x squared. So that's like my part A, right, where it asks me to write the area function. David, are we happy so far?
Yeah.
Okay. Now, I should come up with a domain for this function, right? So what is the smallest possible value for r? Probably 0, right? Because if x is 0, then the area is 0, and that's not a rectangle anymore. And what's the biggest possible length for r? I'm sorry, for x. Jeepers creepers. It's not supposed to be an r there. We're talking about x's, Mr. Kulik. It's a function in terms of x. I just kind of gave away the answer, though. The biggest possible x. R, right? because you'd have r squared minus r squared, which is 0, which gives you another 0 area. If we think about this physically, if x is 0, then like this is my rectangle. That's not a rectangle at all, right? If x is r, then this is my rectangle. Not a rectangle at all, right? So just like physically, that's what that's looking like. So far, so good? Yeah. Okay, so that's like part A. Part B says then we need to find the maximum, or the r that, or I'm sorry, it asks for the directions, say specifically, I want to get the wording the same. The x, or the maximum possible area in terms of r. So I need to find the x that maximizes the area function. So I'm going to take the derivative of this. Now, I'm looking at this and not liking the product and chain rules that are going on here. So I'm going to do a little bit of algebra to reduce, or to make this a little bit easier. So I'm going to think about x as the square root of x squared. And because now this is underneath a square root, I can distribute this through here. Keep in mind that I don't really have to do this. I'm just doing this to get around having to do a product rule, because it'll make the solving a little bit cleaner if this is all just one thing. So now if I take the derivative, no way to get rid of the chain rule. So the derivative of the outside, oops. Four times 1/2 the inner stuff to the negative 1/2 times the derivative of the outer stuff. I'm sorry, of the inner stuff. Everybody okay here? So let's see, I can clean this up a little bit. Boom, boom. So I have 2, and then my numerator over square root stuff, right? Now I'm going to set this equal to 0 and undefined. I'm doing my first derivative test here, or second derivative test, but I'm finding critical points anyways. So where's this going to be undefined? Well, it's going to be undefined anywhere where the denominator is negative or where it's 0, right? So the nice part is, if x is stuck between 0 and r, this part can't be negative, because r squared times x to the 4th can't be negative, because x to the 4th can't be bigger than r to the 4th. Great. And it can't be 0, because the only places this would be 0 is if both the x's were 0, which can't happen, or both the x's were r, can't happen because of the domain. So there's no place where the derivative fails to exist that's inside of the domain for A. So I just need to worry about where it's equal to 0. This is a fraction. When is a fraction equal to 0? When the numerator is 0. So I can ignore the denominator. It's almost like Marcelino's talked about this before.
Right.
Have we talked about this before? I don't remember. Okay, well, excellent. All right, so I got this, right? To get this, to solve this equal to 0, how should I approach this? Okay, well, I might as well do 4, right? Because I can take a 2 out of that also. Okay, that's fine. And then take an x out also, yep. We're solving for x. So then I have x equals 0. And have that, right? Now I can discard the negative result. Why? The domain for x we said had to be greater than 0. So now I can either do a first or second derivative rule here. Or first or second derivative test to check this. Right? To figure out which one is the maximum, which one is the minimum. Better do it. All right. If I plug, we'll do a first derivative test. There's nothing over here, right? And there's nothing bigger than r, so we need to pick a test value in here and a test value in here. Everybody's okay? Let's see. Something that is smaller than r divided by the square root of 2 would be just like r over 2, right? Because the square root of 2 is 1.4-ish. So if I divide by more than that, the number is smaller. If I try plugging this in up here, I'm going to have the 4th root of r over 4 minus, r to the 4th over 4 minus r to the, oh, we're out of time here. Oh, my goodness gracious, guys. Hold on 1 second. Why can we discard 0? Can't be 0, right? So I just need to do a of r over root 2, and that's going to give me my maximum area, because it has to be the maximum. That's fine. Yeah, give me a second to kind of get my wits going. David, is that?
Good question. Yeah, like a lot of times I looked up how to do it, but I didn't know what steps it took to get it. So
Just sometimes having the narrative to go through it also helps.
yeah. Adrian, we'll come to our seat.
Yeah, or come to
Thank you.
I got an update. I'll let you know.
Hey, what's up?